Okay, I think it's time for us to get started on the session. This is Seeing Smaller, Larger, Deeper, but Thinking Bigger, Imaging the Earth's Surface. And I'd like to welcome you to the last session on the last day of the 2022 AGU meeting. My name is Susan Roberts, and I'm the chair for this session. And along with my co-chairs, Ann Meltzer and Ilingasakari, which I hope I pronounced correctly, and our co-convener, Eileen Hoffman, I'd like to thank you for joining us this afternoon. So this union session is an activity of the College of Fellows and the College of Fellows Legacy Committee. And it's the second of two at this meeting. And it's been organized to highlight how transformative discoveries are connected to advances in our ability to image the Earth. The first session highlighted transformative advances in planetary science, study of the deep Earth, and environmental pollution. The speakers in this session will take us on a tour of the Earth. We're starting from the surface, then down through the water column of the dark ocean, beneath the surface, and then finally down to the seafloor. In preparing for the session today, I was really struck by the etymological link between imaging and imagination. By expanding the reach of our senses through imaging technology, we can also expand our imagination to develop a new understanding of our Earth. So to start us off, we will have a pre-recorded presentation by Andrea Donnellan. She was unable to join us in person, but she will be online for the Q&A. And I will briefly bring up the slide for our speakers. So after Andrea, we will have Andoni Lavery and then Larry Mayer.
Good afternoon. I'm Andrea Donnellan. I'm very sorry I'm not able to be there in person. I'm looking forward to this session, and I'll be talking about advances in remote sensing of the Earth's surface, past, present, and future. This should be a very, very long author list, so I stuck to me as first author, but none of this can be done without very large teams of people. I'll be talking about remote sensing of the Earth's surface, drawing, of course, mostly on my own research. But we've been doing it for decades, and it helps enable an understanding of the solid Earth superficial processes, ecosystems, cryosphere, and hydrological processes. I'll be focusing on solid Earth and superficial processes with fires, because those two are intimately related, or they can be, at least in California, where I live and work. And there are also landslides. I'm not going to talk about those here. Remote sensing provides a broader view that can be accomplished by observations in the field. Of course, both are very important, and we need to use both to support the other. Orbiting satellites provide a global systematic view, but I'm also a big champion of airborne campaigns, which provide a regional context with configurable flight paths. Here's just an example of something you can do with remote sensing. It's the Sherman prescribed burn from a few years ago. On the left is a short wavelength infrared image. You can see through to the valley floor. On the right side is a visible image where the valley is socked in by smoke. So we want to look at different frequency bands, different types of measurements in order to study Earth's surface processes. There are a few themes in this talk. I'll be drawing on my own research and also signals that we see in our data. I study crustal deformation. I've been identifying active faults for years. And with geodetic imaging data, you can measure elastic versus inelastic behavior of faults. It's very useful for imaging earthquakes, both from the coseismic and the postseismic motions, as well as the plate boundary processes that lead up to earthquakes, because we have a broad synoptic measurement and view. But we can also see surface disruption in our data. So I'll show you an example of that from a wildfire, but there are also landslides you can see in the data, or you can measure subsidence from aquifer withdrawal. The geodetic imaging methods I will speak to are GNSS, or GPS, Global Navigation Satellite System, INSAR, and UAV-SAR. UAV-SAR is the airborne version of an INSAR radar imager. And also stereo imaging, also known as structure from motion. LiDAR is another excellent way to get topography. Topography is useful for looking at changes present day, but also for looking back into the geologic record. And all these methods then help us address multi-scale spatial and temporal processes. First method I'll talk about is GNSS position time series. And I like this example here. Here's a GPS antenna attached to a receiver, probably elsewhere, bolted into the ground about 10 meters on these drilled brace monuments. And there's a network of stations throughout the globe, but also California, and particularly the coastal area of California along the active faults. And I'll show you some examples of what we can do with those data. But the data are very complicated. We don't just have a simple plate boundary motion. We have long-term velocities, a long-term trend, but we have jumps, normally from earthquakes. And then we have time-dependent motions. We have post-seismic motion here from the El Maricucapa earthquake. Then the Brawley swarm happened, and we have another jump in our data. In the vertical, you can see subsidence, sometimes from groundwater withdrawal or motions, or it can be from magma motions or fluids moving in the earth. And then we can have stable motion. So we can classify those data, and we can also use them in our models. So we can take those velocities. Now these are in a different reference frame. They're in the ITRF reference frame with, I think, a stable North America, but we have shear along the San Andreas Fault. And we can classify common characteristics in the vectors at each station, and we can define the number of classes. So in this case, we've defined 2 classes, and what pops out is the dominant San Andreas Fault. That shows our major plate boundary motion across California. We can separate again into different number of classes. I'm just showing 3 classes here. That means there's 2 boundaries. We still have the dominant San Andreas Fault, although now these classes join up over the San Jacinto Fault, and there's some debate over which is more active in the Southern California region, or more likely to have a large earthquake. And then our second most dominant class or boundary is here in the Eastern California shear zone. This to me is fascinating because it shows us how California is bifurcating. The San Andreas Fault, as you can see, goes around the Big Bend here. So it's geometrically a barrier for plate boundary motions. And so in a sense, California is peeling off up through the Eastern California shear zone, and we can add more faults, which I'll show you compared to other data. So here we've divided into 5 classes. We have the San Andreas Fault, the Eastern California shear zone. Then we start to pull in the San Jacinto Fault and the Elsinore Fault. And if you do more classes, you get more faults that can highlight. So this is a great way to rank faults and understand them. And just to show it's consistent with the seismicity, we have seismicity in the Eastern California shear zone along the San Andreas Fault. You can kind of get a sense of the barrier that the bend of the San Andreas Fault causes. And we have the Elsinore Fault and San Jacinto faults as well, showing up in the seismicity. Since this talk is on past, present, and future, I'll show some of the INSAR that we observed back from ERS-1 radar satellite in 1995 or 1993 to 1995. This is the Northridge earthquake. I had been conducting GPS measurements in that area for my PhD thesis. We had identified active faults that were verging up towards each other across the Ventura Basin. One of those faults broke in the Northridge earthquake and caused this bowing of the ground surface. Here, the fringes for interferometry, you can count up, they show you the amount of uplift. What we're looking at is if the satellite passes the second pass exactly in the same place as the first pass, and the ground doesn't move, then the fringes, and we know the timing of the fringes, overlay exactly. But if the ground moves a little bit, or if the satellite moves a little bit, those fringes will be offset. And that's when we get this interferogram. So it's kind of like oil sitting on the surface of water. We have different colors where the oil is a different thickness. Again, there was 40 centimeters of uplift in the Northridge earthquake, which was illuminating, but we knew from other methods generally that this is what happened. This gave us a much more spatially smooth understanding of the crustal deformation of the area from the Northridge earthquake. What was really interesting to me in that earthquake, though, was the post-seismic motion. So here, the yellow lines are the GPS motions. The fringes are, again, what we see in the radar image. There was 12 centimeters of post-seismic uplift over 2 years. 90% of that motion was aseismic. We added up all the aftershocks mechanisms and computed the displacement that those should show. They showed the exact same pattern as we saw in the GPS, or close to the exact same pattern. And but they were only a fraction of what we measured. We were also looking for viscoelastic relaxation of the lower crust after the earthquake. Instead, it turned out that afterslip was the dominant mechanism, and we were able to easily show that in a model. Spaceborne radar is extremely useful. It gives us a global synoptic view, gives us a very spatially smooth view and systematic repeat measurements. But UAV SARs turned out to be a very powerful platform. It's something I've been working with since about 2009. It's flown on a Gulfstream aircraft from NASA. It's housed in this pod, and you can see here that it's side looking. So it's looking down at a 45-degree angle, or a 27 to 63 degree angular range. It has a swath width of about 15 kilometers. And typically our lines are anywhere about 90 kilometers long. So here's an example from a proposal we submitted in 2008. We were looking at Southern California, southernmost California, and the Napa area, because some of our modeling based on the earlier work I showed that these were active regions and may have earthquakes. Turned out that we had earthquakes in all of these areas. I could talk about it forever, but I'm just going to give one example from the El Mayor-Cucapaw earthquake. The El Mayor-Cucapaw earthquake happened in 2010 in April. It was a magnitude 7.1 earthquake. It ruptured actually in Mexico. At the time, we weren't allowed to image in Mexico. Now Eric Fielding is. So we had a radar swath right at the north end of the rupture, which turned out to be a very interesting place to work. You can't see it too well here, but it was a right lateral fault. So purple is pulling away from California, and the yellow area, which you can't really see under this number here, is the right lateral motion pushing up into California. There was a lot of uplift from that earthquake. The whole Brawley area in the Salton Trough lifted up as a result of that earthquake. We saw a lot of triggered slip on other faults, and I just show some of these here. We had cross faults that showed slip, as well as these faults here. So I've just sort of made a cartoon of how the deformation occurred as a result of the earthquake. And again, a lot of the deformation was triggered slip on other faults. We continued to image the area with UAV SAR after the El Mayor-Cucapaw earthquake, and the UAV SAR turned out to be extremely powerful. GPS is very nice in that it gives us very detailed time series, but with a network spacing of stations of 10 kilometers or more, we miss a lot of these subtle details that we saw in the UAV SAR. So in the coseismic motion, the area to the northeast moved southeast, and the area to the west moved up to the northwest. But then there were details of additional rupture. So using automated edge detection techniques, you can find the additional faults that slipped in kind of a fracture pattern north of the north tip of the El Mayor-Cucapaw rupture. And then we watched that evolve for years, about 7 years. And these cross faults and the area to the north of the rupture continued to evolve and concentrate its slip on surfaces. We had been looking for how stress would transfer from the El Mayor-Cucapaw rupture up to the Elsinore fault. But what we found instead is that slip occurred in the area between those two faults and just dissipated over time. So we see a logarithmic decay there. I don't know that any slip was transferred to the Elsinore fault. I think it's longer term driving stresses that cause each of these faults to slip and break. And with the edge detection, again, we see the Yuha fault and we see the cross fault joining the El Mayor-Cucapaw rupture to the Elsinore fault. And again, most of that can be explained by just afterslip on the main shock rupture with a little bit of deformation at the crack tip and a velocity strengthening layer thickness of about 2 kilometers. So I'll switch gears here for a moment, because in the UAV SAR data, we see other things. We were imaging Southern California to understand tectonic processes, but we've had a lot of wildfires occur where we are mapping. Here's just one example from the Thomas Fire Montecito debris flows. You can see in the radar image, just the polarimetry. So now we're in a single image, we're not in an image pair. You can see the fire scar quite well. And if we zoom in and then do an interferogram, we see where the ground is disrupted, both from the wildfire and the debris flows. So purple is disrupted. And so I now enhance those colors. You can see the wildfires and the debris flows, excuse me, and then we've correlated them with measurements, and we posted those products to our GeoGateway site. We also did some change detection with optical imagery as well, and from that then you could additionally separate out the debris flow from the disrupted area, because we see the debris flows quite nicely, but we don't see the disrupted area quite as well. So that was past and present. Now I will talk about the future. In 2017, the Decadal Survey came out, and they recommended designated observables and targeted observables. Designated observables are to be implemented in the near future. Targeted observables aren't ready to be done yet. They need maturing before the technology and the science is ready to turn it into an observing system. So they recommended, in what I'm talking about, relation to what I'm talking about, surface deformation and change, and surface topography and vegetation. Surface deformation and change is NISAR and a follow-on mission, so it's a radar type mission. Surface topography and vegetation needs to be matured for a future observing system. And both are important in fusing the data for earthquake research and other types of research, wildfires, debris flow, land surface processes, and ecosystems as well. The NISAR mission is a joint mission between the Indian Space Agency and NASA, the US. It is scheduled to launch in 2024. It's in testing right now, will be shipped to India soon. Again, it's a collaboration between NASA and ISRO. It's an all-weather day-night imaging satellite of nearly the entire land surface and ice masses of the Earth. Measurements will be repeated 4 to 6 times per month. The resolution will be 5 to 10 meters, and products are expected to be available 1 to 2 days after observation. It has a very large deployable mesh antenna when it's flying, and it's an L-band and it's an S-band instrument. Here's just an example of what we can do with a radar. You've seen several from UAVSAR as well as ERS-1. This is the Ridgecrest earthquake. I did not do this work. Red is right lateral slip to the southeast. Blue is right lateral slip up to the northwest. Again, it was 2 earthquakes. You can see it here. There was a 6.4 earthquake followed by a magnitude 7.1 earthquake. We'll have these nice, beautiful radar images. We can also see surface disruption. So you can look at correlations between before and after images and find areas that are disrupted as well as smoothly deforming as a result of an earthquake. And then there were the targeted observables that I mentioned. I will talk about the surface topography and vegetation study, which I led with an outstanding team of people. We wrote a report, which you can find on this Decadal Science webpage, Observing Earth's Changing Surface Topography and Vegetation Structure, a framework for the decade. And so our job was to identify gaps and understand what we need to do in order to mature the technology and the science in order to have an observing system or architecture ready for the next decadal survey and then ready for implementation. We broke the study up into technologies, which we looked at were radar, LiDAR, stereo imaging, and information systems, which need to bind all this together. And the science we looked at was solid earth, ecosystems, cryosphere, hydrology, coastal processes, and then other applications. This was roughly in alignment with what the decadal survey recommended, but we changed our science disciplines just a small amount. One of the most important things that came out of the study, which we did with our team, but we also had community input through workshops, polls, vetting of the white paper, et cetera, was that we need systematic repeat measurements, and that's not offered by a lot of measurements. So we need to address the science needs, which are looking at processes, which are looking at change. So we need good baseline measurements, and then we need follow-on measurements. So we divided up parameters. The other part of our job was to put out a preliminary science and applications traceability matrix with all of these different disciplines. There are a lot of different needs. So we distilled that into one table because that provides a focus then for a future architecture. We had aspirational needs and we had threshold needs that we addressed. We had our median need between all the different disciplines, but then we also called out the most stringent need from each discipline. So the disciplines here are by initial, cryosphere, hydrology, solid earth, etc. Generally, though, the community would like 90% of the globe covered. The threshold need is about 55% of the earth. We need a latency of 5 days in order to do things like disaster response and rapid science response, but people could get away with 2-month type interval of observations. Ideally, we'd like the system to last forever or almost a decade, but 3 years is a median need that we could get away with. We want a weekly repeat frequency or sub-weekly repeat frequency, but we could get away with quarterly. We don't want to do worse than that because we need the annual observation, the annual signals, seasonal signals to be removed from our data. We want 1 meter type observations with a vertical accuracy of 20 centimeters. Same with vegetation vertical resolution. And then we were also asked to look at shallow bathymetry, shallow water bathymetry, and the max depth we need to observe to fill gaps is about 25 meters. We need good geolocation accuracy, and then we want to measure rate of change to about 5 centimeters per year. Where do we want these measurements? Well, of course, everywhere. So we can't necessarily do everywhere all the time. So we want a global baseline map of topography and vegetation structure. But then we can focus on specific areas, the active plate boundary, for example, for surface topography, rivers and coasts for shallow water bathymetry, the cryosphere for snow and ice, and then the more temperate regions, the non-desert regions for vegetation structure. I'll talk really quick about my own instrument, which is an airborne stereo imager, which could be a pathfinder for a spaceborne stereo imager. The goal is to mature it into an end-to-end operational system. But because it's airborne, it's targeted, it has flexible data collection, but it's also not global. So that's the drawback. It has about an 80 centimeter ground sample distance, a 12-kilometer wide swath, and can image about 5,200 kilometers in a 6-hour flight. And to show you one example very quick of what we can do with it, here's our image, our stereo image of the Ridgecrest rupture, which I showed you in the radar. This is the field measurements along the rupture. And we took a profile across the fault of vertical locations in the point cloud, and you can see the rupture and the offset from that. Also in the image, you can see the offset on the ground from that earthquake. So to leave you with a summary, I wanted to leave an image of the Mammoth Lakes area showing that you can discern individual trees in at least sparse conifer forested type areas. So we can do vegetation structure with stereo imagery, but obviously LiDAR is also a powerful technique in their radar applications. Remote sensing of the Earth's surface is best accomplished through a combination of airborne and spaceborne platforms and different technologies because they measure different parts of processes. They measure different temporal and spatial scales of those processes. We need accurate repeat measurements to measure temporal changes. This came up again and again and again in our FSTV study. And a baseline is useful for measuring future change.
Also, I'll thank Andrea in absence for her presentation. And I'm going to ask our tech people. I didn't see Andrea online. Is that correct? Okay, I think we have a couple of minutes in case anybody wants to make a comment. I'd say we have a small crowd here, so we can be informal, I think, and certainly open it up if anyone would like to. Yes.
I am here. They just put me in as a panelist.
Oh, okay. Hi, Andrea. So I'm just checking with our audience to see if anybody has any questions for you.
And very sorry I couldn't be there in person. I had to come back for something.
Okay, well, I'm not seeing any questions online, and so unless someone has a question here, I don't know if you would like to add anything since you're with us here, Andrea?
No, I hope I covered most of it in the talk. So-
Yeah. Oh, here we are. We do have a question. So the microphone's over there.
Hi, Andrea. I'm just wondering if you have any plans on combining stereo optical with radar image for imaging vegetation, forests.
Could you introduce yourself, please?
Oh,
It's Yunling Lu,
I'm
right?
of JPL. I'm a colleague of
Okay.
Andrea's.
So I would like to see that be done. It's not in my expertise. I do want to combine for sure the optical imagery and SWIR imagery with the polarimetry for wildfires, which we have observed. And the visible and the SWIR for the Mauna Loa eruption, which I didn't show here, and then compare that to the GLSEN data. So we want to make the data available so somebody will do it, but it's probably a little bit outside of my expertise to do it myself.
Okay, and we have another question, Larry?
I was just your SVT mission, or if that's a mission, I was intrigued by the shallow bathymetry. What the sensor is a LiDAR sensor, or is it?
We don't know yet.
You don't know yet. Okay.
So STV is a targeted observable. The designated observables are ready to be architected and launched in the near future. Targeted observables were deemed not mature enough yet without investment to create an architecture for a mission. And NASA added the shallow water bathymetry. You can measure it to some extent with ISAT, with LiDAR. So that's one method. But we're studying that now and hope to come up with a better understanding of that in the next 3 years.
Okay, great. Thanks.
Okay, well, thank you again, Andrea. I will bring up the next presentation, and the next speaker is Andone Lavery.
Hello, everyone. Thank you so much for being here so late on a Friday afternoon. So I am going to be talking about sort of my view on what the transparent ocean is. And it's really a talk about imaging the ocean with sound. And while our task was to look at the past, the present, and the future, I have to admit my talk is very much more on the present and the future than on the past. All right. We just heard from Andrea about the advances in imaging surface processes. And honestly, when I look at what they're doing, I am jealous. And I think of how much technology they have to throw at this. But it turns out that our planet is mostly covered in water, and these techniques don't work very well for imaging far below the surface in the water. And so the ocean is largely unexplored. And so finding techniques that allow us to look into that volume is really what my research is about. Having said that, you can still use satellite remote sensing to get some really very useful data about the ocean surface. You can get surface salinity, you can get surface temperature, you can get sea surface height, you can get, there's a lot of information in satellite images of the surface of the ocean. And I use those all the time to guide my research. Here, for example, you see a paper. This is data that was collected on the right. You see satellite images of the east coast of the US. This is the Gulf Stream, and you can see these warm core rings peeling off. And so some of the research from just looking at these images has been to look at things like how many warm core rings are impinging on the east coast of the United States per year. And there's this suggestion, for example, that the number of warm core rings that have been generated is increasing in time. However, what the impact of those are on what's below them, that's the part that I'm interested in. So it turns out that the ocean is really very dark. So here you see basically light penetration at different wavelengths. And you can see that in the open ocean, you're basically talking about light penetration down to about 200 meters. In coastal waters, which are murkier, you basically have penetration down to 50 meters. However, the ocean is fairly transparent to sound. So what you see on the right is a figure which basically shows acoustic attenuation as a function of frequency. And well, I think the first and probably the most important thing that you want to look at is the units on attenuation. It's a dB per kilometer. Okay, so we've gone from tens of meters to kilometers. And, you know, it's very frequency dependent. You can see that at what I'm going to call low frequencies, sort of below about 1 kilohertz, you can see that attenuation is very low. However, as you get up into the mid frequencies between 1 and 10 kilohertz, you begin to see a little more attenuation, but you can still do a pretty good job imaging and probing the ocean. Once you get up above about, 10, 20, 50 kilohertz, you're going to be looking at maybe 1 kilometer. And so I think the other important thing is you want to look at the wavelength. Okay, so there's a big difference between the speed of light and the speed of water, the speed of sound in water. Speed of sound is slow, and the wavelengths are relatively long. You were talking here, centimeters, meters, as opposed to hundreds of nanometers. And the result of that is that the ocean is essentially like trying to drive a self-driving car in the snow with no GPS and no communication and hoping that you're going to get there okay. It's a featureless, and on top of that, it's a pretty featureless environment. And so what it really turns out is that the best way to probe the ocean is to use acoustics. This is a figure from a paper by Bruce Howe in 2019, and I just put it here. This is a pretty low frequency transmission, but the idea is just to illustrate how far sound can go in the ocean. Okay, now obviously for every gain, there's a challenge, and the challenge is interpreting those signals. I am going to put a plug for the next speaker. So the next speaker, Larry Mayer, is going to be talking about imaging the seafloor. And I'm not going to talk too much about that. I'm going to leave that for him. But you can begin to get information about the seafloor. It's not at the resolution that we would like, but from using acoustic techniques, different kinds of multi-beams and side-scan sonars, you can get much higher resolution imaging of the seafloor. But the boundaries are going to be all his, and he can talk about those, and he can tell you about why you would want to image the seafloor. And there's my insane plug for you, Larry. Meanwhile, I want to get back to basics a little bit. And so what do I mean by imaging the ocean interior with sound? And generally speaking, I sort of compartmentalize it into passive acoustics, where you put a hydrophone out and you just listen, and active acoustics, where you actually go out there and you put a signal in the water and you use it to actually target something. Okay, my research is very much more on the active acoustic side and not on the passive acoustic side, but there are some very important applications of passive acoustics. Okay, so smorgasbord. Okay, so I took this figure, which was from Bruce Howe's paper, and then I just started adding things. I tried to use the same color scheme, so it looked like it would be his responsibility, but I have added many things. And on the passive side, you could use passive acoustic monitoring to look at anthropogenic sounds, things like military sonars, ship noise. These are sort of anthropogenic sources of sound. Biological sources of sound, looking at marine mammals. You could look at snapping shrimp, fish burps and other things. Or natural sounds such as, breaking up of ice, waves, wind, rain, storms, these kinds of things. On the active side, You can do the very low frequency, long range tomographic type experiments. And there you get at more average properties of the ocean because you're averaging over a fairly long path length. And sound, you know, sound is complicated how it behaves in the ocean. It doesn't travel in straight lines. It refracts, it diffracts, it scatters, and it attenuates. And understanding the signals that you get is not straightforward. It's also, acoustics is pretty much one of the only ways right now that we have for communication. So if you want to communicate with an AUV, you're going to be using sound. Navigation, you're going to be using sound. My research is mostly in this sort of imaging and ranging area, and a lot of this talk is going to focus on stuff that we do down in the bottom left-hand corner of that figure. Okay, so this is, I'm going to talk very briefly about passive acoustic monitoring. It is not my area of expertise, but it is important. And this is a figure from Sophie Van Paris. This is a 2021, and this is basically a NOAA representation of passive acoustic monitoring. And what you see here are different sources of noise in the ocean. It could be ship noise, seismic surveys, wind farms, just echo sounders or recreational boats making noise. It could be weather, earthquakes, biological organisms, and the size of the acoustic spheres of influence, you can see more or less represent how important those different processes are. In terms of scales and sort of if you're trying to use passive acoustic monitoring to sort of track, locate, enumerate different types of organisms, well, you know, things like fish are going to you're going to be able to hear them out to a range of about 100 meters. Whereas, you know, baleen whales, such as blue whales or fin whales, you're going to be able to detect out to 20 or 200 kilometers. So you're going to do much better at tracking marine mammals, depending on the frequencies and their source levels. But the frequencies is really important. Okay, like I said, going back, I'm actually going to focus on that bottom left-hand corner, talking about imaging, sort of the ocean interior. Okay, so this is sort of an iconic figure. This is from a colleague, Jim Moom. This was data collected in 2001, published in 2003. And this basically shows breaking internal wave off the Oregon continental shelf. And so you can think of the ocean as, you know, very crudely in the summer, you have a lot of stratification, you have surface warming of the surface waters. And so you have a sort of a warm layer on top, you have a cool layer underneath, and then you have some disturbance and you end up, you know, it could be an internal tide interacting with topography, and you get these nonlinear internal waves, which result in shear instabilities and ultimately in mixing, right? It's a really important process in the ocean to understand where mixing is happening. And, you know, this doesn't just happen here and there. This is an experiment in 2006. This was an experiment where enough instruments were put in the water to cause sea level rise. And what you see on the right is internal waves, again, generated at the shelf break. And what you see there is that going back to Jim Moom's measurements, this was done at one frequency. And so there's only so much interpretation you can do when you use a single frequency to try to interpret acoustics in the ocean. So one of the advances that's happened over the last 10 or 15 years is the move to broadband acoustics, so that you can actually sort of do spectral resolution of different processes. And so this is one of the first experiments where we basically had spectral resolution, distinguishing between scattering of sound from small zooplankton and actual microstructure in the ocean. So sound will basically scatter from any kind of an acoustic impedance. That impedance could be a bubble, it could be a particle, or it could be just a small change in the temperature and salinity of the ocean, which result in a change in the gradient and the sound speed, which in turn scatter sound. And so changing scales, because one of the things that you can do with acoustics is, you know, thinking bigger or looking smaller, you can resolve some pretty small scales over large regions. Okay, and so one of the experiments that we've been going back to the Connecticut River. It's like the Connecticut River is like my backyard experiment, and this is looking out from the Connecticut River into the Long Island Sound. The ship that you see out there is the Neil Armstrong. And one of the things that we've been really interested in is the generation of these plume fronts. And imaging them using a whole variety of different techniques. And I can tell you the captain of the Armstrong was not happy. This was the maiden voyage of the Armstrong, which I scratched with that small boat there where we came alongside, and it was only 8 meters deep. And that's not a lot for a ship with of that kind of draft. So the captain was pretty much not my favorite person. Well, I was not the captain's favorite person. Anyway, so what did we see? We deployed some vehicles and we put acoustic sonars, basically echo sounders, on the vehicles. And this is a vehicle that's going under the plume front. And what you see is the signal associated to the plume is mostly scattering from bubbles. And the bubbles are basically hiding the scattering from the microstructure. That basically the scattering is dominated by bubbles. And again, you can do spectral resolution to decide what part of that scattering is microstructure and what part of it is actually bubbles. When we first went out there, we were interested in how much mixing was happening at these fronts, but we found that instead it became a bubble experiment. However, in parts of the Connecticut River, so this is again, if you look at the scale on the left, it's 8 meters deep. And this is basically where the salt, where the fresh water from the Connecticut River comes out into Long Island Sound, and you have these shear instabilities which are generated. And these shear instabilities are evolving really fast. They're about 2 meters tall. They have a wavelength of about 20 meters, and they are evolving in the time periods of seconds. And so it's really hard to image these with any kind of sort of in situ sensor. Using acoustics, you can actually really begin to sort of resolve things like the dissipation rate of salinity variance at the scales that it's being generated at. And so, that was pretty exciting. Let's change scale. One of the things that I've been focusing on, this is my backyard. This is the New England shelf break. And one of the reasons that we do a lot of our work there is that we have the Coastal Pioneer Array. So we have a number of moorings out there that are collecting sort of basic oceanographic data. And we've been really interested in things like how the Gulf Stream and the warm core rings interact with the shelf break, how it changes the ecology of the shelf break, and how it changes mixing at the shelf break, and then going off the shelf break and into the slope and sort of looking at things like the interaction of these sort of mesoscale features with the ocean twilight zone. Okay, so this is basically the New England shelf break. This is data collected in March. We've collected a lot of data in March, which is insane out there because it's really not very favorable in terms of going out and doing a cruise in March off the New England shelf. But we have a lot of March data. And what we find is that there's very little stratification on the shelf in March. And so what happens is that the shelf break front can really creep up over the shelf. And this has some real significant biological implications, because what you see is the top panel is basically 18 kilohertz and the second panel is 38 kilohertz. And at 18 kilohertz, you're getting a lot of scattering. So you're basically imaging what the front looks like. If you see all of those, I'm not sure if my mouse is going to work. Over here, this is the front. These are temperature and salinity stratification that you're seeing. This is where the front is coming up onto the shelf. And you can see here where the head of the front is right there. All of this is biology. This is biology that wouldn't be there if it wasn't sliding in with the front. This is another example. This is 3 or 4 years later, March 2021. And you're seeing the same thing. You're seeing, this is the shelf break front. We actually had a shelf break streamer here. So you can see that there's a bit of a bulge of this shelf break front here. And again, you see all this biology hiding in the slope waters coming up over the shelf. Turns out that we think that's probably some combination of squid and mackerel based on the acoustic analysis. But the other thing that you see is you see that using these acoustic techniques, you can sort of begin to see this really, you can see all these little waves which are happening. And when we happen to have a multi-beam out there, this is a 7100 kilohertz multi-beam. And again, you see here these shear instabilities which are happening on these fronts, which of course result in mixing. Okay, so if you move off the shelf now and you go down into the slope water, so now the water is 3,000 meters deep, and we have to take some pretty different approaches to understanding. In this case, we're sort of more interested in sort of the mesopelagic habitats, and one of the things that we've been really interested in is how much biomass is migrating, right? And with that biomass, what contribution that biomass has to the carbon cycle. And so we've developed a whole series of instruments. And today I'm actually going to talk mostly about this bioacoustics mooring that we've had out there for about a year, collecting acoustic data now for about a year. But it's part of a network and a series of cruises that involve the development of this new ultra broadband system that we call Deep Sea. We have Mesobot, which is one of the first instruments that basically is designed to sample the midwater. Many of our vehicles go down deep, they look down at the bottom, or they're sort of surface associated, but there's not many vehicles that can really do a good job at sampling and holding place in the midwater. But first, I'm going to actually show we're not the only people interested in the mesopelagic. These are slides that my colleague Kelly Benoit Bird sent me. She's at MBARI, and they are interested in broadly similar things. They have the advantage of having a cabled observatory, which means that they get real-time data. And this is something, oh my goodness, that would be a dream come true. But in any case, we have to go out every 6 months and change batteries on moorings and retrieve data, which is both costly and not as effective. But in any case, this is their system, and it's a great system. And I'm going to show you some of her results. Whoops. This is just sort of a day in the life of the West Coast mesopelagic. And you can see, and this is spanning a number of different seasons, and you can see that there are vast differences in what the deep sound scattering layer looks like at different times of the year. You can see that how much biomass migrates is very seasonally dependent. You can see that just how much backscatter there is very seasonally dependent. For example, you can see that in this on the bottom right-hand corner, there's basically no migration happening. So this is in May. It basically looks like migration has stopped. Whereas if you look in early April, you can see that almost the entire water column migrates. This has real implications for, carbon cycling. The other nice thing that they had on their Mars observatory was they had a hydrophone, so they could actually listen to different types of organisms and when they were around. And one of the things that they found was that if you look at this deep sound scattering layer that you're seeing here, when there were these Rizzo dolphins present, the sound scattering layer basically broke up. So that's a really nice result there. But like I said, we are working on this sort of ocean twilight zone observation network. It is not a cabled network, unfortunately. It is more than 200 kilometers offshore. It's in 4,000 meters of water. And so wouldn't it be nice to have underwater GPS and data transmission, broadband data transmission rates, which we don't have. And that would be something that would be very nice. In any case, I'm going to focus right now on that bioacoustic mooring that's in the middle. This is just 6 days. Like I said, we have a year of data. And one of the really fascinating results that actually my student Zhao Zhong has been working on is that you can see that the deep sound scattering layer is actually being modulated by the internal tides in the region. And this modulation is actually not insignificant. You can see that the modulation is on the order of 50 or 60 meters. So there's a very significant interaction in the deep set. This is the non-migrating deep sound scattering layer being modulated by these internal tides. In addition to that, we're quantifying how much biomass is migrating and also what the structure and timing of those migrations is. And so that's something that's work in progress. That deep mooring also has, it's a split beam system, which means that you can actually locate targets. So you can get their target strengths and you can actually locate the targets. And so we're using a combination of individual target strengths and their swimming patterns to begin to identify what the different types of organisms are that we're looking at. And again, that's, so I'm gonna just show one more slide on this. When we were out there putting out moorings, which is anyway, it is, we crossed over the north wall of the Gulf Stream. And these data was so fascinating that it has prompted proposal writing, frantic proposal writing since. So we're hoping that we'll be able to go out and study this some more. But anyway, this is the Gulf Stream currents. These arrows represent currents. And I'm just going to show you a slice of acoustic data where you see this blue line. And what you see there, okay, so over here, this is on the slope water, so north of the Gulf Stream, and you can see a pretty standard sort of deep sound scattering layer. As the evening wears on, you can see, the day goes on and the evening comes in, you can see that the migration starts and it goes up. And then about 2 hours later, you can see that all of this biomass is beginning to get subducted under the Gulf Stream water. At first, when I saw this, I thought it was the downward migration, but that's the middle of the night. And so all of this structure that you're seeing here is due to the interaction of the deep sound scattering layer and the migrating organisms with the north wall of the Gulf Stream. And that is definitely something we're very interested in. Okay, so I'm going to end with just a few slides that my colleague YT Lin gave me. He's been developing, he's really got a very broad view of how to acoustically image basically the East Coast of the United States. So he's been developing this thing called the Acoustic Telescope, which is a 25 hydrophone array, which you can put in deep water. And what it can do is it can basically locate targets in 3D or locate sounds in 3D. It could be whales, it could be rainfall, it could be ships, it could be submarines or anything else, volcanoes, any source of sound. It does a really good job at locating. Now, you cannot emphasize what an enormous effort and what a feat this is. It's this acoustic telescope is virtually impossible to deploy. It's 25 meters in diameter. It's very, very long. You have to deploy it with the arms in and then use acoustic releases to bring the arms out once it's deployed in deep water. And so anyway, so this was deployed for the first time in summer 2021. And so this is where all the hydrophones are here on the left. And here it's just sort of looking at how the performance of the system in locating and tracking a particular target. And the other thing that this acoustic telescope allows us to do is really improve your signal to noise when you sort of coherently do the beamforming with all of the different hydrophones. Okay, and so the view that we have right now is that we would have one of these telescopes sort of scattered up and down sort of the East Coast. Each one of those telescopes actually has a surface expression where you actually can communicate via satellite and get the data real time. And so all of a sudden, we're really beginning to look at sort of an observatory type system. And so summary and conclusions. Okay, summary and conclusions. These are my summary and conclusions. Acoustics is hard, you know, it's wavelengths are long, speed of sound is slow, acoustic signals are complicated and noisy, but it is in fact one of the only remote sensing tools we have in the ocean at this point. And so we need to figure out how to use it to our advantage. And so humans as very visual creatures, we sort of look at these signals, and I don't know if you can read that, but it's really something we all say. Thank you, and happy to take any questions. And recorded that in the airplane, so I would play it for you, but it was actually kind of loud. There's a lot of background noise, but those are my conclusions. Happy to take questions. I won't point.
Yes. Yeah, thank you so much, Anthony. And I have to say, she flew in this morning just to give this talk. So really an extra round of applause for Anthony. Yeah, and so we do have time for questions, and please use the microphone and introduce yourself.
So I'm Larry, the next speaker. So thank you, that was great. So one is just a really probably naive question. I think I know the answer, but when you had the mooring with the huge migration, there was a lot of biomass still staying down near the bottom. Is that just simply a separation of species, or do some subset of the same species actually not migrate?
Those are excellent questions, and we are throwing all kinds of tools at that. So this system, this deep sea system that I talked to you about, it has eDNA sensors, it has cameras, it has broadband acoustics, multi-beams. And some of the questions that we're trying to answer are, to what extent is there that species? Is it by species? Is it by size? Is it by, I don't have an answer for you right now.
I thought everybody knew the answer.
Yeah,
to that.
no.
I was-
However, what I can tell you, and I think something I meant to say during the talk and I didn't, is that there's a tendency, we want to interpret acoustics as biomass. We want to look at this and say there's more biomass there than there is there. And I think one of the things that, almost the first time that I went out to study the ocean twilight zone, I immediately noticed that the deep sound scattering layer is in a different location at different frequencies. And anybody who's looked at data, the first thing, all kinds of alarms should be going off if your biomass is frequency dependent.
Yeah, and that actually is my next question, because on the slope water coming up, that's not biology.
It's not,
It's
and
probably not turbulence, I would think.
no, and so I'm guessing there's got to be, well, I don't know if sediment can get pulled. You mean pulled up to 100 meters above the sea?
It can when you have internal waves breaking,
Yeah.
but.
But then
no,
there's
I-
turbulence, right? And there's definitely stratification.
Yeah, but this is, an argument we have, the non-acoustics, where I shouldn't call myself a non-acoustician, but with the real acousticians is that I think, as you know, with Liz's work, we're seeing a lot of just pure temperature and salinity.
Yep.
Density contrasts in itself that are creating amazing targets. I think more than we ever believed
Right.
we'd see.
Yeah, no, I think that there's anytime there's a gradient,
Exactly.
you're likely to, if you pick the right wavelength of sound, you will see some scattering.
Exactly.
Anthony, can I ask one question before, because we have a little extra time? And so this is probably a very naive question, but I was really taken with the bubbles. And so I know for biology, a lot of times bubbles are really important, and people have been using bubble screens, to turn away fish. So I'm wondering, can you use bubbles as a, sort of a very strong acoustic signal for biology?
Absolutely. Most of what we're seeing in the deep sound scattering layer, I'm guessing, is swim bladder fish. Yeah, small, the myctophids, but they're lanternfish and so on, but they're small swim
Yeah,
bladder
the
fish.
swim bladder is the gift.
It is a gift.
Yes.
Yes.
Hello. First thing that I have to recognize is that all of this take me by surprise. So I don't know much about this stuff. So I'm learning here. So thank you for the very didactic presentation. I come from Europe. So my question is there equivalent work in Europe or different tendencies there?
Yes, there is. There are a couple of actually, I don't think they call it the ocean twilight zone. That's such an American take on it. I think they call it the mesopelagic, right? And so, yes, there are a couple of big mesopelagic initiatives. One of the big things is, we have this ecosystem that we really haven't managed yet to really exploit, right? There are a few countries now that have fishing permits to go fish the mesopelagic. And I think one of the things that the whole community is trying to do is to get ahead and to really understand that system before we don't sustainably exploit it.
Thank you.
And the sonars are all European, but they stole that idea from me. They came and sat in my office.
Well, thank you again, Anthony. Okay, so we have our last speaker for this session, and that's Larry Mayer. I will bring up his presentation.
So I'll start talking already before the presentation comes up, because I wanted to tell a story that you've heard and these guys have heard, but maybe not the other two people out here have heard. So this is not the last time that I've been the last speaker. And early in my graduate student career, I was the last speaker at the last session of the AGU. And at the beginning of that session, there were only about 20 people in the room. That was great. And then as it went on and on, there were 10, 9, and finally it was the chairman, who was John Orcott, myself, and one other person. In those days, they used to have a bottle of wine for the last speaker. And John says, well, this is silly. Let's just, the three of us just sit around and we'll drink the bottle of wine. And so we gather around, and he thanks the guy very much for staying, he said, and the guy says, well, he says, I'm actually really here just to clean up the room. So I'm hoping that you guys aren't here to clean up the room. No, okay, all right. So then I'm okay. All right, I actually I have a note here because there's a quote that I wanted to read, because I was really intrigued by the note that the conveners wrote to describe the section, and you said much of the output of geoscience is intensely visual. And I think this ties in tremendously with Andrea and with Andoni said also, that it's true. I mean, we're a product of our senses, and it's absolutely right, because 30% of the neurons in the brain are devoted to sight, and over 60% of the brain is involved in vision in some way. So we're just tremendously visual people. And this is the way we've always explored. I mean, in ancient times, people just looked up, used their vision, and came to all kinds of amazing conclusions about how the earth worked and astronomy and things like that. And when we got the technology, we were able to turn those senses around and look back down on the earth again, using those visual cues and those visual senses. And as Andrea described, doing amazing things, what I like to call the geospatial context for the earth, with all kinds of, again, Andrea went into the details of what we can derive from this information about earth movement, things we can derive about the cryosphere and the movement of ice, quantitative information like getting out digital terrain models, and even thematic information. And Andrea led into some of that too. So it's just really phenomenal what we can do. But really any 5-year-old now can just go into Google Earth and push a button and get an amazing image of the earth. It's just trivial. Andrea will get very upset with me for saying that, but it's simple to get that kind of imagery, earth, and to map and to get that visual exploration. But that's, as Andoni pointed out, that's really just about the blue and the green portion of the earth, and maybe some concrete too. What about that 3/4 of the earth that's blue? And of course, if we turn the same sensors there, we get nothing like that, for exactly the reasons that Andoni talked to us about, that light just doesn't penetrate into the ocean. We can't use electromagnetic waves. Again, we can learn about the sea surface, but that's as far as we can go. And so we have to, we can't use the vision system. And what I'm going to do is build up an argument about how we can go back and try to, through a whole bunch of other senses, come back to visualizing what's going on. In my case, where I'm focusing is on the seafloor. And the first way to do it is to actually penetrate way down into the system. We have the technology to do that. We can bring a vehicle, a remotely operated vehicle with optical sensors and electromagnetic waves, get it close to the seafloor. But we're limited by, Andoni and I were talking about the stupid physics, that again, light just doesn't travel far. So we'd have to do it to image the seafloor at the scale that we can do a Google Earth. We'd have to get within a few meters of the seafloor, and the images would only have a very small area. And I was once asked by Google Earth, what would it take to do a real Google Ocean, not a broad scale, but what would it take to build a Google Ocean at the scale of Google Earth? And we can figure out how many meters we can cover, a couple of meters, a couple of square meters, maybe 4 square meters in an image, how long it would take, what the area of the ocean it would take. What is that? You're the mathematician. A lot of images, 600 trillion or something like that. And what it would take to do that is hundreds of millions of years. So it's just not the answer. And we've had to fall back to other senses then to explore the seafloor, because we have to be able to somehow penetrate through that bothersome water. And what we did originally is turn to touch. And the way we first started to measure the seafloor was with just a hunk of lead at the end of a rope, lead line. That's statue that was taken from an Egyptian tomb, 2000 BC. If I go to the next picture I was able to find, it was actually 3,500 years later. It's a carving from the Thames River. Again, measuring the depth of the seafloor, same technology, 3,500 years, no change. But if I jump 500 years later, 1940, what are they doing? Exactly the same thing. So 4,000 years, no change in technology. We were just feeling where the bottom was, not very accurate, as you can imagine. And what you'll see is the progression of data density along the bottom. That's in megabytes per hour there. So you see no change in 4,000 years. But then, well, not being able to see the next slide. I never know what's coming here. Yeah, so this was used to make the earliest maps. This is a map that Matthew Fontaine Murray, kind of the father of American oceanography, made 180 lead line measurements across the entire Atlantic. And he then used his imagination and connected the dots, draw this contour. He was trying to start a company to put telegraph cables across the Atlantic. So he used a liberal interpretation and made a big plateau there and said, that's Telegraph Plateau. You see, it's no problem to put a telegraph cable across the Atlantic. Took them about 30 years to actually succeed because it was a lot deeper than they thought it was. But starting really in between the First and the Second World War, actually developed for the first time, I think, really based on the Titanic sinking to look forward. People realize, again, we can now go away from touch and start using sound, as Andoni explained, how sound travels so well in the ocean, and echo sounders were developed. Simple what we call single beam echo sounders, sends out one ping of sound that spreads widely on the seafloor. We get a bounce back when it hits something that whose physical properties change significantly. And if we know how fast sound travels in water, and we do through the work of people like Andoni, we can find how far away it is. And so this is obviously much more accurate, much quicker than a hunk of lead at the end of a rope. And you see, we've now been able to increase the data density by 3 or 4 orders of magnitude. But we pay a price for that. And that's that sound spreads in a big wide beam, and we only get one answer back. We have no angular resolution anywhere in that. And so we just get a single measure of depth in a kind of very blurry way. But now we've gone to using a sense that's a little more sensitive, the sense of sound. Years and years of that kind of data collection, ships coming out of Scripps here, collecting single beam bathymetric data, and again, connecting the dots of this blurry picture of what the seafloor is. And we got what was this was in 1999, the best depiction of what the seafloor looked like off Southern California. And this is what the kind of information we had for most of the world ocean. And so what we're looking at really is we're starting to use our vision when we have a contour map like this, but it's a very blurry picture that's distorted by the lateral averaging of that single beam echo sounder and the sparse nature of the data. If we would apply modern visualization techniques to that sparse data, this is a 200 by 200 kilometer piece of seafloor and 4,000 meters of water. That's what it would look like. There's no sense really applying those techniques to it. It's again, this blurry picture because of sparse measurements that each measurement in its own right is laterally averaged. And then, really starting in the 80s, 90s, maybe something came along called multi-beam sonar. And this was really a tremendous leap in technology. Instead of using a single transducer or a small array of transducers, this used very directional arrays, something called the Mills-T or a Mills-Cross, where you use an array that's elongated in the along ship direction to produce a very narrow beam in the fore-aft direction of the ship and a wide swath across the seafloor. So that's what the transmit beam looks like. That's it looking down from the top. And then you use an orthogonal array. And that array, you form beams. You use a technique they developed for radar, forming beams. So you're looking in individual directions. And that does that instantaneously across the entire swath, forms many beams that are elongate in the fore-aft, in the along ship direction, narrow in the across ship direction, and it can form actually hundreds of them. And what you end up at the end of the day is the cross product of the two. And we end up with a series of very precise measurements across a wide swath of the seafloor. So we can have, in some cases, hundreds of individual depth measurements now across water depths that are 4 or 5 times, or across a swath that's 4 to 5 times the water depth, all at once. And so it was a revolutionary change in our ability to map the seafloor. We went from these broad swaths of a single beam that had one depth somewhere in there with no angular resolution to now hundreds of individual measurements across a wide swath, each one with very, very high, excuse me, resolution. And as you can see, the data density went from that first 3 orders of magnitude to now 4, 5, 6, 7, 8 orders of magnitude. Tremendous amount of dense data coming in. That's really giving us a very precise picture of what the seafloor depths look like. And if we look back at our 200 by 200 kilometer piece of seafloor, and we see what does just a single swath of a ship, surface ship coming through with a multi-beam sonar look like, it looks like that. And so you see what a difference a swath makes. And now we can finally get to the resolution where we can look at processes and really start to understand the geology. I mean, people who look at this, Bernie here will look at this and know that that's a geo. This is something that's been exposed to sea level. We really start understanding processes. We're mapping at the scale that we need to address all the things that Andoni had in her slide, all the reasons we mapped the seafloor that I won't go into, I don't think. But what this does allow us to return now for bathymetric data from that acoustic, from that sound sense, to now we can look at it in a visual sense and come back to that original statement that I'm sure you wrote, Sue, about, let me see, much of the output of geoscience is intensely visual, and it is. And this is what we've been able to return through the combination of multi-beam sonar and visualization techniques. And so we can take this picture that we had in 1999 of the best imagery we had of the seafloor off Southern California, spent a couple of months with multi-beam sonars mapping from there, and we turned that picture into that picture. And you can see really provides an amazing new perspective and many new insights and many new applications. It's not just the depth that we can measure from the multi-beam sonar. We can also look at the amplitude of the sound coming back, something we call backscatter. Andoni talks about backscatter in the water column. We talk about backscatter from the seafloor, and that has some hint, not necessarily a one-to-one mapping, but it gives us some implication about what the nature of the seafloor is. So it's not just where the seafloor is, but also what the seafloor is. This is bathymetry off Hawaii. This is Diamond Head, Pearl Harbor out here. We can see this down about 800 meters. This is about 40 meters up here. See the nice changes in depth. They had for years been dredging in Pearl Harbor and dumping the dredge materials out here. And the Navy was interested in the impact of those dredge materials. From this bathymetry, you can see no evidence of the dredging. You see a lot of these are real features. These are big sand waves or sediment bed forms indicating a fast current that comes around the island. But where was all the dredge material? If we look at the backscatter, though, instead, what we see is you can actually here at 500-600 meters see each one of these circles is an individual dredge site where a scowl, is that what we call it? A barge goes out and opens up its hoppers and dumps material on the seafloor because the acoustic properties of the material differed from the surrounding material. And here where the fast current is, we can see there it was all blended together. But this is all so thin that the bathymetry couldn't resolve it, but we can see it. So this adds a whole nother dimension to what we can understand and look at in the seafloor. And here's that slide. I thought I had that slide in there somewhere for why we do all this. Of course, a lot of our work is driven by safety and navigation. It's a very bad day when the ship runs aground. We can measure habitats and, I'll go back to that, habitats and ecosystems from the backscatter. The bathymetry is very critical for determining where deep ocean currents move and cannot move. So that kind of deep circulation is critical for climate modeling, as is just the general roughness of the seafloor, because that controls the turbulence and how heat is distributed through the water column. Natural hazards, cables, pipelines, tsunami inundation, earth processes, national security, maritime heritage, and the one I love the best, all the things we don't know, because as I'll make a point in a few minutes, only 23.6% of the ocean is mapped with this sort of technology. Okay, so just to give a little more information about why we map. It's something I just never realized till I got into this business. You don't think about it in this day of planes and everything, but still 98% of the imports by weight come by sea. And so when a ship runs aground, it's a very bad day for the economy. It's a bad day for the environment. It's a bad day for the captain. It's a bad day for everybody. So a lot of effort is to make sure that ships can navigate safely. To give you an indication of the size of the problem, that's the scale. This is the Harmony of the Seas, a large passenger vessel relative to the U.S. Capitol building. So we have these ships with 40-meter drafts. So it's a big, big, serious problem. National security and sovereignty. You can imagine from a national security perspective, those countries that have submarines have to navigate in a three-dimensional world. We've had several incidents of late where U.S. submarines have run into uncharted seamounts. There are hundreds of thousands of seamounts that are uncharted. And it's a huge problem that has to be looked at. But from a sovereignty perspective or a sovereign rights perspective, there's something called the Law of the Sea Treaty, which is a remarkable constitution for the oceans. And in it, there is one little article, just 617 words, that redefine the continental shelf, what we geologists and geophysicists know very well. It defines it in a juridical sense, in a legal sense. And based on that definition, allows a coastal state to extend its sovereign rights over resources of the seabed and the subsoil. So really about oil and gas. The way you establish the limits of that legal continental shelf by measuring the depth and the shape of the seafloor. You have to find where the foot of the continental slope is. You need to find the 2,500-meter contour. You need to see how thick the sediments are. So it's a very geologically and geophysically oriented process. And the bottom line is to do it, you have to map the seafloor. So many, many nations now have been mapping the seafloor in support of it. And the US now has done more than 3 million square kilometers of new multi-beam data collection to support its establishment of the limits of its continental shelf. And I'm very proud, and this goes back to the last session, that the US has made all of its data publicly available. And hopefully many other countries will start doing that too. But every time we went out there, we'd have kind of the before picture, what things looked like before, what it looked like after, a radical difference in terms of what it looks like, but also very different because the foot of the slope with this detailed multi-beam data can be put way out here. So each time we went and made detailed measurements, it allowed us to extend the limits of sovereign rights for the US, as many other countries too. We also have been doing a lot of mapping up around Greenland and other people mapping around Antarctica to actually use the shape of the features on the seafloor to look at the history of the Greenland ice sheet, but also understand the processes that are starting to be responsible for its rapid melting and global sea level rise. And that is very much controlled by what the bathymetry looks like, where there are sills that can, in this case, block an inner sill that blocks the inflow of warm Atlantic waters, protecting the ice tongue, or in the case of this area, Petermann Glacier, where there's a sill, but it's so deep that it allows that warm water to come in, and the Petermann ice tongue has been receding and receding and receding. So we're starting to understand the controls of that process, and again, controlled very much by the bathymetry. Maritime heritage, just spectacular imagery that we could never do optically, or divers would have to feel their way around these things. Hundreds of thousands, if not millions of wrecks, kind of preserving the heritage of mankind. And again, acoustics is the key mapping to get that kind of information out in a very productive way. I don't have to focus on the water column. Andoni did such a beautiful job of that, but as our sonars, as they're mapping, also look at the water column. She showed you great examples of that. Gas has been something that, gas heaps has been something that really has drawn a lot of attention late. Gas is a wonderful scatterer, those bubbles, and just tremendous ability to map natural gas heaps and also map unnatural gas heaps. Many of the techniques that we're using to visualize this were developed when Deepwater Horizon spill took place, and we were down there trying to figure out what was going on. So quickly pressed the wonderful acoustics that people like Andoni developed and turned that into a visualization environment that we can see what's going on. And this has now become both a prospecting tool and a tool for looking at man-made leaks too. These are all natural seeps in the Gulf of Mexico that surrounded the Deepwater Horizon seep. So we have the tools basically to map all of our planet, not just the brown and the and the green part, but the blue part too. But how much of that have we done? If we take a look at the National Geophysical, or what they call now, the National Center for Environmental Information, used to be called National Geophysical Data Center. And they collect as much of the multi-beam sonar data they can around the world and look at the distribution. It looks like in lots of places we have lots of coverage, but this is on a global scale, and those swaths, they have to show them a pixel of a swath would be or a pixel on a map like this would be 200 kilometers or so. And that would be a very large swath. So if we zoom in, we see that really even those areas that look like they're fully covered, they're very, very poorly covered. And in 2017, I'm going to start there for a reason, only 6% of the global ocean was mapped with multi-beam sonar. We've developed tools to impress upon us just how little the seafloor is mapped. This is the area where the MH370 went down when they first went to look for the wreck of the plane off Australia. They sent a bunch of autonomous underwater vehicles because they had to get close to see something as small as a plane wreck. And it turns out that none of the autonomous underwater vehicles could see the bottom because the global estimates of depth were more than 1,000 meters off. It was 1,000 meters deeper than they thought it was. And that's because if you look in this area, 1,800 kilometers by 1,100 kilometers, the only multi-beam sonar data was where these yellow tracks were. Almost none of it mapped at all in any kind of accuracy. Well, what would it take to map the entire world ocean? With current technology, we know the rough distribution of depths, and I'm going to ignore the shallow waters, less than 200 meters, because that takes an inordinate amount of time. We'll leave that to individual nations or other techniques, satellite techniques. But if we just looked at deeper than 200 meters, and we'll look at some end members of kind of optimistic, where you get a swath that's 4 times the water depth, and you can go 10 knots, or more conservative, 3.5 times the water depth each swath, and only go 7 knots. It would take about between 70,000 and 127,000 ship days. I have a cost here that's a couple of years old. It's probably more like $55,000 a day now. And so it'd be between 3 to 5 billion, say 5, well, let's say 4 to 6 billion dollars now. And so we say, well, we'll never do it. How are we going to do that? Who's going to pay 3 to 5 billion dollars to map something? Well, you know, we do that all the time. We map Mars at much better resolution than the Earth. All of Mars is mapped at 20-meter resolution, a lot of it at 1-meter resolution. And every Mars mission costs $2 to $3 billion. And I love the idea. I just love the idea that we're mapping Mars. We should be mapping Mars, but you think we might be able to take one of those missions and turn it back to Earth and look at our own planet and try to see our own planet mapped at that level of resolution. There is growing momentum. There's something called the Seabed 2030 project out there that's trying to facilitate the global mapping of the ocean by 2030. It's an aspirational goal, but it's helping. As I said, we started in 2017 with 6% of the ocean covered. By 2022, we're actually at 23.6 now. Now, a lot of that has been just discovering data that's been hidden in draws and things like that. We really have the big effort now of trying to collect new data. And this is going to be the hope of looking ahead. I think we'll see a lot of technologies that are going to improve the data we collect, increased bandwidth, chirp multi-beams. We're going to calibrate the system so the backscatter means more, get new geometries maybe, so we really get angles, all kinds of angles at the same time. A lot of improvements in the software and the sonar design itself, better measurements of uncertainty and automated processing tools. All that's great, but none of that's going to help us with the Seabed 2030 kind of goals, except for the last two. And that's the idea of using autonomous delivery systems, kind of a force multiplier, and maybe even going as far as synthetic aperture or sparse arrays. So if we look at the costs of a typical oceanographic research vessel, we'll say $55,000 a day now. Most of that cost is the crew and the fuel. And if we can now reduce a lot of those with some kind of autonomous platform, and my dream is this giant barge with a 30-meter by I'll accept 20 on the receive end array, and it's doable. I know it's doable. We can reduce crew costs, fuel costs, and consumables tremendously. We can cut the cost down probably in a third. We've been focusing on autonomous systems to learn how to use those. Some small ones that we play with in terms of developing software, but some larger ones that are really getting serious in terms of being capable and a force multiplier. We've recently been doing a lot of work with something called the DRIX. This is a wave piercing vehicle that can go up to 14 knots and have an endurance of 7 days, about 3,000 kilometers. And so it has, this is the, what was that show with the beach? What was that show? Nobody remember the show with the people running on the beach? That's the shot there. Beach something. I don't remember what it was. But this is really, now a system like that is not cheap, but it costs a lot less than a ship at $55,000 a day. We're also looking at a 72 foot or 22 meter long sail drone that's equipped with a deep water multi-beam. And we've had its first trials and a transit from San Francisco to Hawaii, collecting beautiful mapping data all the way. It's a wonderful platform for mapping data because it's very, very quiet. We're seeing how that works out in terms of long time. The real issues there are going to be what the costs of operating these systems are. And it's just finished up now 51 days in the Aleutians. We're quite excited to see that coming along. We're seeing other force multipliers. We're seeing lots of distribution of black boxes on yachts and things like that, crowdsourced bathymetry, and even the development of echo sounding floats. Imagine every Argo float with an echo sounder on it. And that's being developed with a company called SeaTrek. And finally, this concept, which I'm very excited about, it's a tough one. And this is where Andoni will kind of get the willies. The idea of having maybe 40, 50 of these floats, maybe, or small little ASVs, each one of them with a receiver over 40, 50 kilometer spacing, few sound sources in them, few of them are transmitters, and we basically create a distributed sparse array, which in theory, with a 40 kilometer footprint, would give us meter-like resolution on the seafloor over a 40 kilometer swath. The whole problem there is how well we can quantify the water column, because it's a tomography experiment. And so we always end the talk with a sunset. This is actually from the Arctic. So it's actually a sunrise and a sunset all at once. Sun came up, popped down. But to me, it was very symbolic, because I think with respect to mapping the seafloor, and I think each of the speakers today, it's really not the end. It's really the beginning. So I got to thank you guys, the four of you, five. You're real heroes. So I'm going to thank you all for staying. And you're not here to clean the room, are you? You're not here to clean the room, no? Not really. Okay. And we won't ask you to do that. Okay. Thank you. And I thank Bernie and Annette too, who promised me they'd come. So that was very nice.
Yeah, so thank you so much, Larry. And I want to thank all of our speakers today, because this was really, I think the creme de la creme. And we were so thrilled as the organizers to get such a terrific lineup for our presentations today. And I do hope, I believe it's being recorded, so I hope that it lives on. Tell your friends, what a great series of talks this is. And I hope we have a really good, a long tail, I guess I would say, to our presentation today. But we do have time for questions. So if anyone would like to ask Larry a question, and then maybe we can open it up to all three of our speakers.
Yep. Okay.
And please do use the microphone and introduce yourself.
I'm Joan Masó from CREAF in Barcelona. I'm a raster guy, so I would like that you clarify the resolution of this global map. What is the current resolution we have? We have all seen these deep things with the Atlantic mountains. I don't remember the name, but you know what I mean.
Yep.
So the current thing, if I remember correctly, that's 2 degrees resolution, something like that. What is or 2 minute resolution, I believe it was. So with the technology that you have presented, what could be the resolution
Yeah,
for the
so-
map? And I understand, I suppose the resolution varies with the deep, so that is, maybe there is not a direct answer.
There's a direct kind of proportional answer because the resolution is going to be very dependent on the water depth. That's one variable for the sonar itself. And it's going to be very dependent on the length of the sonar array and the frequency. There's all these three things you have to trade off. So we can build very, very high resolutions that get centimetric systems that get centimetric resolution that'll operate in 50 meters of water or depth. They'll be at very high frequency. And if we can put a long array on it, we can, I mean, some of those, you saw those wrecks, those images of the wrecks, those are systems that have 5 centimeter, 10 centimeter resolution in 20 meters of water. So that's doable, but everything scales. So if I go to 5,000 meters of water, I'm now talking about having to use a much lower frequency because of the slide Andoni showed, where sound won't try, the sound, the 455 kilohertz sound that I use to get the wreck won't go more than 50 meters or 100 meters if I'm lucky. I have to use 12 kilohertz to go 5,000 meters or maybe 30 kilohertz. And at that point, I'm going to have a resolution on the seafloor of maybe 70 meters or something in terms of lateral resolution. The vertical resolution is always really good. We don't worry about that, but it's the lateral resolution that's the real constraint. And that's why this idea of a barge that had a 30-meter long 12 kilohertz array could actually get resolution on the order of 7 to 10 meters on the seafloor. And this sparse array that I talked about, 40 kilometers long, made up of individual things, could get down to a meter resolution in theory, but you have to be able to correct for all the water paths. So, but the global map, I want to show these global maps we see all the time. Oh, you're not seeing it. No, that's okay. The big global maps that you see like that, those are mostly come from satellite derived bathymetry, which I didn't go into. And it's a magical thing. It's remarkable. It's the fact that the surface of the ocean will respond to seamounts, which will have a lot of mass, so the gravitational vectors start pointing toward it, and it'll respond to big deep holes, trenches. The vectors will go the other way. And so you get these deviations in the sea surface that reflect the changes in bathymetry, but that's at a very, very, what Bernie knows, 10, 15 kilometer resolution laterally, and it can be off by hundreds of meters as it was with the MH370. So that's the big picture that we get like that. And that's great for where the big seamounts are and where the deep trenches are in the ridge crest. But beyond that, we need to get the acoustic information.
Considering that the shuttle radar topographic mission gave us the whole wall at 30 meters, having the depth at 70 meters seems really a good.
Yes, boy, if we can have the
Amazing.
global ocean at 70 meters, I would be delighted. The seabed 2030 has a cascading scale of resolutions. And what we're saying in the deepest waters, 5,000 meters or above, we'll be happy with 800 meter resolution, very, very sparse resolution, just so that we only have to pass over areas once. And then 3,000 or 5,000 we're down to 400 meters and 200 meters, and 100 meter resolution is the finest for the deeper than 200 meters of water. We can do better than that, but that's to help us achieve that goal for the first pass.
Great, thank you very much.
Thank you.
Oh, all right, we have a race for the next question.
Guess first. You're the guest.
Hi, my name is Morgan Wolf. I'm an undergraduate student at the University of Toronto. I guess what I'm curious about is, even as bathymetric mapping tools continue to improve in resolution and efficiency, we still seem to run into the problem of, with individual scientists or institutions in charge of mapping and deciding where to map, you start to see this problem where the interesting features get mapped multiple times, more than once, but there are big swaths of ocean that are still basically unknown. And
This is a great question.
Yeah,
And when the ocean exploration program started, it started with President Clinton had a panel. And the panel recommended that we start with the highest resolution multi-beam systems we can have, start in the corner of the Northwest Pacific and map the entire ocean, just map blindly map. And it's the right way to do it for just the reason you say, but we got to write proposals. We got, and it's always going to be the features, the seamount, the interesting features that attract attention.
Yeah.
And so they eventually came to a compromise, what they called boxes and sticks. So you'd have a few interesting things, but you'd make sure you collect information in between. And that's what CBET 2030 is the way it's evolving. There are a lot of people who transit, go one place to another, get from one interesting place to the next. And they don't necessarily turn their mapping systems on. But CBET 2030 is both encouraging them to do that. So companies like Fugro are doing that all the time now, donating the data. And CBET 2030 will even help pay for the collection of data on those kinds of transits. But you're absolutely right. There's a huge bias in them. I think it's a common psychological issue.
Yeah. Focusing on like the things we know are there and
Yeah,
just.
exactly. Yeah. Well,
Okay.
again, part of that comes back to the fact that people have to write proposals.
Yeah.
And, am I going to write a proposal to go somewhere nobody knows anything about? On the basis that I'll discover something great? Well, odds are you might, but the funding
Can't
agency
say
is a
for
little
sure.
too conservative for that. Yeah, that's a great question.
Thanks.
Larry and Tony Lever here.
Yes. And where are you from?
I'm from the Woods Hole Oceanographic Institution. And I have a question to you about your costing, your $2 to $3 billion cost
Mhm.
to map the seafloor. And I guess my question is, how much does one of these systems cost? Because mapping the seafloor once for a $2 or $3 billion ticket isn't going to get you answers about, ecosystems and how they're changing and so on and so forth. This is obviously, as with satellites, we get repeat data. You want repeat data. Wouldn't you be better off putting instruments on ships of opportunity that will be doing the same trajectory, the same path over and over and over?
Well, it's very related to that question. And I say it depends. Yes, you would. And I would love to see both happening. But I guess my bias would be that first thing I got to know is what's there. If I have 75% of the seafloor totally unmapped, how do I start thinking about what I have to protect, what I have to manage, what I have to repeat in terms of a measurement? I would love to do both experiments at the same time. So certainly, and we are putting we're putting systems of opportunity, or we're putting systems on vessels of opportunity, not multi-beam systems, but digital data collection systems. They tend to run the same paths over and over again. So we will be getting that repeat data in the corridors that they run, but it may be that other corridors that we don't know about are much more important in terms of understanding global change.
So how many of our oceanographic ships actually have these multi-beams?
Almost all of the larger vessels and some of the smaller vessels too now, because the cost is really coming down for the smaller vessels. So I can't think of a UNOS vessel except for the Endeavor, which doesn't, and the replacement for the Endeavor will. And many of them are putting more than one on now, multiple frequencies, which is really nice.
Having said that, I've been on the Armstrong many, many times. I think we've only had the multi-beam on once.
That's a different issue. It has a multi-beam. And there was a time where NSF insisted that they be turned on all the time. And that seems to have gone away. And I suspect that's mostly due to pressure from the regulatory side, because the marine mammal impacts, which I think we can clearly demonstrate are nil for the multi-beams, still hasn't been proven to the regulators yet.
So that brings me to a question about your distributed networks. How many sound sources would you have to put out to know their location well enough to actually do the kind of tomography that you're talking about?
Yeah, so this is from work at Lincoln Labs. They did the theoretical look at this, and they had 3 sound sources and 40 receivers for that sparse array. Of course, those are on surface platforms, and so their position is known and their timing is known perfectly because they can see the satellites. I've been thinking about replacing it with these profiling floats. And the beauty there is that, again, the float, when it's on the surface, will see the satellite, know its position. And so the big unknown is the water column. So if you go through a profile, you now collect the water, you have 40 of these, tell them all to sink, come back up. We collect the water column over 40 of these, all talk to the satellite, know their position, do the ping, or many pings. And so this is kind of pie in the sky, really.
It is, but just to sort of get you thinking, for the Ocean Twilight Zone Network, we've put out 3 sources,
Mhm.
sort of one close to the New England sea mounts, one at Bermuda, and one close to the New England shelf break. And they're sort of in the SOFAR channel, and they're about 250 hertz. So the sources are out there. So all you need are the receivers now.
Well, yeah, 250 kilohertz is probably 250 kilohertz or 250 hertz. Yeah. Yeah. So that's a little low frequency. So I might be seeing a little too far below that. Oh, one more.
Maybe just a final question about the networks. So you were discussing is exactly this oversampling of the same areas. How important are the networks of that allows data access to what has been collected? I believe in Europe there was something called CDataNet that was exactly doing that. I believe I played with
So
that a little bit.
EMODnet
Was the one. Yes, you are right.
Yeah, EMODnet.
So,
Yeah, no, these are critical, and it's been a tough battle, but it's I think Europe is now at the lead of open data. Again, the US has been very good about it for most of its data sources. We have to start convincing non-European and non-US partners to make their data available too. And you know, people would argue there's strategic and security reasons, but that's only at some scale. So I think it's at some scale, everybody should find a place they're comfortable with to make the data available.
It is also a way to demonstrate how fragmented it is. I was really amazing when I was playing with that. I had no idea how fragmented this.
Yeah,
this
it's
is.
absolutely true.
Hmm.
Okay, again, thank you.
Yeah, so thanks our speakers again, and thank you for joining us. I think we had a really rich discussion with our very small group, but really enjoyed the talks. And I think, you know, certainly for some of us, these discussions will continue. So take a look at the AGU site. There is for the College of Fellows, if you want to follow the legacy program and future activities. Thank you so much.